Recording start. Okay. So hi everyone. Welcome to this week 11 problem solving session for this NPTEL course on combinatorics. Uh, Sorry for the inconvenience because initially this lecture was scheduled on last Sunday, but due to some unavoidable circumstances, I need to travel somewhere and still I'm outside of campus. So there may be some connectivity issue in between. So you can uh, stop me at that point if there is some connectivity issue. Okay, so let's start. Let me share my screen and start. Okay, so screen start now. Uh, Tension notes. So this should be here. Yes, you can see my screen.
Yes.
Can you? Yes. Okay. So let's start. Huh. So combinatorics. Okay. So question. So let's quickly recall what we have done in this week. So we started with one side lemma. So what is that? That says that if X is a finite set and G is a subgroup of G is a subgroup of the symmetric group on symmetries of Y, then this says that okay, let me explain. So I guess one side we discussed last time as well. So recall. Huh. So let's start recalling. So first first one is this uh, one side lemma. So can you say what is this? Help me in recalling.
So if we have a finite set Y
Yes,
and there's a subgroup G of the symmetries of Y, then
yes,
for the permutations in G are to be fixed. I will
yes.
fixed some
The
elements.
the cardinality of the orbit space is
Yeah,
sum of the one.
all the fixes of the elements.
Yes. So we began with this. Then what else? Then after this, we did a theorem which is corollary of this result, one-side theorem, which says that if G is a symmetries of the finite set X, then the number of G inequivalent n coloring of X is given by summation 1 over order of G. Then and sorry, the number of G. Okay, let me write. So what is this? This theorem says that if G is group of symmetries of a finite set X, then number of G inequivalent n colorings of X is given by 1 over order of G summation pi belongs to G n to the power C pi, where C pi denotes a number of cycles in the permutation pi. So this is basically just its corollary, which is more or less obvious, because if you are in an orbit space, then in each orbit everything same should be like same colored. Otherwise, this is not G invariant. Otherwise, this is not G invariant coloring. So for each orbit, we have one choice of color. So number of permutation, many colors. Number of cycles, many colors. So with this, then we define this this cycle induction monomial. So what is that? So if pi is a permutation, let's say pi belongs to some symmetric group Sn on n symbols. So then we define this Z pi, which is called cycle induction monomial. Cycle induction
I
monomial.
think it was cycle index monomial.
Okay, cycle index monomial. Okay, so maybe I'm okay. So cycle index monomial. So cycle index monomial, which is defined as Z1 to the power C1, Z2 to the power C2, so on so on, Zk to the power Ck. So where what is Ci? Ci is C1 is number of cycles of length 1, C2 is number of cycles of length 2, and so on. Ck is number of cycles of length k. Okay, so this is cycle index monomial, and then we define this cycle index polynomial for a group G. So what is that? Given a group G, subgroup of Sx symmetries of X, we define the cycle index polynomial as Zg, which is defined as 1 over order of G summation pi belongs to G, and then cycle index monomial corresponding to this permutation pi. So yeah, so this is all. Then we go to Polya's theorem. Now let's not write in detail, just speak. And if you are if you don't know anything, you can ask me at that point. So what is Polya's theorem? Can you tell me?
Uh, so
Huh.
let
X is an
some
uh,
X be a, yeah,
X.
the n set,
Huh.
and G be a group of symmetries of that set. Uh,
Yes.
and then for a set of some colors,
Let
uh,
C be set of colors. Let's say R1, R2, Rn. Let's
uh,
say yeah, these are
then
colors.
for tuple that indicates the number of inequivalent colorings under
Okay. Eta.
the use of some number of those colors, there
Yes.
was a function that maps from that set to that colors, basically a coloring of the whatever the set is.
Yes, you are correct. So if you have these colors, then this eta I1, I2, In denotes the number of inequivalent coloring in which R1 appears I1 times, R2 appears I2 times, Rn appears In times, right? So number of inequivalent colorings of X in which R1 color appears I1 times, and so on, so on. R2 appears I2 times, so on, so on. Then we define this power series or polynomial depends on number of colors. Here I choose finite colors, so it is a polynomial. So in multivariable R1, R2, Rn, this is summation I1 plus I2. Sorry, I should write I1. There some should be n. I can write in that way also. I1 over I2, so on, so on. And this is number of inequivalent colorings times R1 to the power I1, R2 to the power I2, so on, so on, Rn to the power In. So we will do several problems related to this. This is Polya's theorem. But the interesting thing is this, that this is same as this cycle index This is the Polias theorem, which says that this polynomial or power series is same as this cycle index polynomial with this variable R1 plus R2 plus Rn, then their square sum, then their cube sum. This is all. So their fourth power sum, so on, so on. So this is okay. So this is the Polias theorem. Then what we did? Then we go to species, I guess. Did something before that? I guess after this we introduce species. So species is basically a function. Are you familiar with abstract language or?
No,
Okay. So are you familiar with this category stuffs or all these things?
no, no.
Oh,
I'm looking at that alongside with that lecture. I'm not familiar
okay,
with
fine.
them previously.
Okay, no problem. So then we can leave this category setup. We can just state as he stated in lectures. So, so what is a species? So species is a rule basically. Species is a rule which assigns with following property. Let's say with following property. So first one is that for each finite set U, you have a finite set Fu. For each finite set U, we have a finite set Fu. Then for each bijection sigma mapping U to V of finite set, we have a bijection. I should say in categorical setup, what I mean by bijection, that is a monomorphism plus epimorphism, because in arbitrary category, this injection and surjection does not make sense. Because you may or may not have kernel and images are there. But in this setup, we are their bijection makes sense. So I am saying just bijection. We have a bijection uh, for each bijection sigma mapping U to V of finite sets. We have a bijection of corresponding F structures. Sigma mapping sigma mapping Fu to F. Species F, I should say, is a rule with following properties. For each finite set U, we have a finite set Fu. For each bijection sigma mapping U to V of finite set, we have a bijection F sigma mapping Fu to Fv. Then, okay. So then what else? Then we have the normal composition rules. If sigma mapping U to V and tau mapping V to W, then then F of sigma O tau is F sigma O F tau. And fourth one is if U to U we have some identity map of a set, then Fu to Fu we have this one should be also, which is F of identity of U should be also identity of F of U. So these are the all conditions. So this is basically the definition of a functor which I needs, which is like a morphism between categories. So and this is all. So then what we see various examples of this thing, and we'll see various example in here as well. Then we see transport of structures. So what is transport of a structure? So can you recall?
It was uh, it was a mapping that takes basically a relabeling of the structure if in the sense that if it is some sort of graph, then a transport basically relevels it, or in general, it's a bijection that preserves some structural
Yes.
properties.
Yeah, but this is not precise one which I okay. So this says that basically if we have two sets, let's say U and V, then a transport from U to V is a map or morphism F from FU to FV, which comes from a set theoretic map from U to V. FU to FV can have FU can have any combinatorial structure. FV can also have same combinatorial structure, but it is saying that this map should come from the set theoretic map from U to V. Are you getting?
Yes, yes,
Yes, that is the what it says. So transport of a structure is a like. So do I need? Okay, let me write. So U comma V finite sets and F mapping U to V bijection. Then there is a function FF mapping FU to FV. And this function FF is called transport of F along F small f. Is called, there is a function is called transport of F along small f. So this is precisely the definition of a what functor, basically corresponding to any morphism in the domain category. You have a morphism in the codomain category. So this is what I was saying. Then what we did, uh, then we defined this thing, exponential generating series corresponding to, for species. For species, what is this? Can you recall? If f is a species, then the exponential generating series is defined as summation n greater than equals 0 fn x to the power n by n factorial. And what is fn? Fn is cardinality of this thing, f on n set, basically number of f structure on n set, right?
yes,
This is exponential generating series for species. And there is another isomorphism type generating series for species, right?
yes. That is the ordinary generating function.
But in their coefficient are different. What are them? Can you recall? Species.
It was the equivalence classes, F
Yes,
of one,
yes,
yeah.
yes. So if f is a species define define uh, isomorphism type generating series as summation n greater than 0 equals to 0 fn tilde x to the power n. And what is fn tilde? Fn tilde is equals to cardinality of what set?
The isomorphism types on
Yes, yes,
the inset by F.
yes. F1 to up to n modulo some equivalence relation. This equivalence relation I am defining. Tilde is defined as how? As
Uh,
s comma t belongs to f of this set, let's say. Then s is equivalent to t if there exists a map of sets n set, a map pies, let's say, from this n set 1 to up to n to n set 1 to up to n, such that such that such that f pi f of how I should write pi s f pi of s should be t, then they are said to be equivalent. These two s and t f structure are said to be equivalent. So this is the definition of isomorphism type generating series. Then what else? What else we did?
Uh, then we looked at some of the, I guess we also looked at before some of the uh, examples of the
Yeah, examples, let's leave this because examples we will do here also. So then apart
cycle
from
indexes.
yeah, cycle index series, and that is, yeah, that is basically a definition, nothing more than. I am not going to do any problem of
Then
this related. Yeah. So then
then
we define
it's
some operation, I
operation.
guess,
Yeah. Yeah.
operation on a species, which are basically addition. First one is addition, which is basically disjoint union. Second one is uh, should be product of a species, which is basically taking two sets and taking two subsets of the set U and then taking uh, F structure on U1 and G structure on U2. And then we define compositions, which also called substitution, I guess they. So substitution, I guess this is what. So 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 that means first we define a G structure on the set U and then define F structure on the set GU, treating as this as a set basically, each point as an element. So this is all, I guess. So let's go to the problem. Then we define
The
then we derivation we also define, right?
yeah, yeah.
And then derivation. Yes. So all these things are there. So let's go to problem and see what we can do. So let's start with some basic problems and then go to good problems. So first question. So this is the figure. Uh, you have one ball here, then two balls below this ball, then three balls below this ball, then four balls below this ball, then five balls below this ball. So these are 15 balls, I guess, no? Says 3, 4, 3, 7, 1, 2, 3, 3, 3 is 6, 4, 10, 5, 15. Yes, these are 15 balls. So question is saying that 15 balls are put in a triangular array. Put in a triangular array as in figure. As in figure, how many different arrays can be made with three distinct colors. Colors if array is free to rotate. So have you understood the problem? What he's saying?
Yes.
So 15 balls are arranged in this way, what I have drawn. So then he's asking that the problem is asking that how many different arrays can be made with three distinct colors if array is free to rotate. Basically, this is this array. Na? If you closely observe this, so this is first triangle, exterior triangle, then another triangle into its interior. So basically, this is this thing. Na? One triangle, another triangle, right? Something like this. Because
Yes.
so how many balls playing in first triangle? One ball, two ball, and three balls between them. Similarly here, three, and this is a three balls here and three balls here. So these are 15 balls. Let's name them. Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right. So these are 15 balls. So how many different arrays can be made with three distinct colors if array is free to rotate? So can you think? Hint is use one side lemma.
So
So you have to identify a given group and this three distinct color if array is free to rotate. Basically, two colorings are same if they are same up to rotation. So you have to find out means each orbit is different orbit spaces are different coloring. So we have to count number of orbits. So you have to identify given set and the given group, right?
okay, so uh
This type of problem we also did in last problem solving session, right? One side lemma related.
yeah.
Yeah. So given set is clear. Set is 15 elements which are 15 balls basically. I'm writing them as a numbers, 15 balls. What is a group? Group is given by this rotation, right?
Yes. So there will be for one element is the identity, then the next element will rotate it. So we can do 120 degree rotations three times.
Yes,
Yes. So
120, then two. So
yeah.
basically what? So we can write it in a permutation form, na? That will be more easier because we have seen in one theorem above. This says
Yes.
that if G is a symmetric group, then symmetries of X, then basically that is a corollary of one side lemma, which I write here. Yes, this one reason. Second one, maybe we can do directly by one side. Yeah, first let's do by second one, then we'll do one side by also. Both are same basically, na?
Yes.
Are you getting or not?
Yes.
So
Am I audible?
yes, you are
Yes.
audible.
Yeah.
So can you tell me what is the group? You are saying group is rotation by 0 degree, rotation by 120 degree, and rotation by 240 degree, right? Yeah.
Yes.
So this
There's
is the
we can also do a we can't no, reflection is not allowed, right? Only rotations. So you are
only
just
rotation is,
yes, yes.
yeah, this is the complete group. So can you see now what is this going to be? What is the how to use one side lemma basically? What is the fix of rho naught basically? Fix of rho naught. Everything is fixed under rho naught, right?
Yeah. Everything is
So,
switched.
so this is how much? So this is 15. Cardinality of
Uh,
fixed point of rho naught is 15
yeah,
basically.
15.
Yes. Now, so now each one have three choices basically. Each one have three choices, right? Each coordinate like each ball have three choices. Either it can be colored with red color, it
Yeah,
can be
yeah.
colored. Yeah. So basically, how many colorings we have for this one?
So we have
We can
we
three to
can
the power
yeah,
3 to
yeah,
the power 15.
yeah.
So so number of possible colorings equals 3 to the power 15. Similarly, for Fix point, fix of this one, uh, row 1, row 1. Fix of row 1. What is fix of row 1? Sorry, row 120.
So do we first need to write the uh, mm, permutation cycles,
We can write in that way also. That is also fine. We can write.
or
What is
we,
row 0?
or we can also I'm asking what is the standard way? Should we always write the permutations in a cyclic?
I
Uh,
prefer doing in a permutation way
yeah. Okay. Okay.
because that is more easier. I can use that theorem, the corollary of one side lemma, which is more easier to use than one side lemma, basically, in this case at least. So what is row 0 basically? Row 0 is, well, let's write them in a permutation form. Row 0 is basically identity permutation. Then row 120 is what? 121 goes to 5, and then 5 goes to 9, and 9 goes to 1. This is closed. 2 goes to 6, 6 goes to 10. This is closed. 3 goes to 3 goes to 7, 3 goes to 7, 7 goes to 11, and then fourth one, 4 goes to 8, 8 goes to 12. Then last one, what is row 240? This is where? This is what? 1
So
goes to 9.
yeah,
Yes,
5
1
goes
goes
to
to
1.
1 goes to 9, 9 goes to 5,
Yeah.
and 5 goes to 1. Then 2 goes to 10, 2 goes to 10, 10 goes to where?
6,
Yes. Similarly,
11,
3 goes to 11, and 11 goes to 7.
7.
And then 4 goes to 8, and sorry, 4 goes to 8 as what I
4
did.
goes to 12.
4 goes to 12, and 12 goes to 8.
Yeah.
Yes, this is the all. Then if you use this theorem, which I mentioned here, so this says that basically if G is a group of symmetries of a finite set X, then number of G inequivalent n coloring of X is given by 1 over
Mm.
order of G, pi belong to G, n to the power C pi, and that you can use
Yeah.
directly. So what is that?
So that will be 3 to the power 4.
That is equals to number of G inequivalent 3 colorings is equals to 1 over what is the order of G, that is 3, and then summation of what? Summation pi belongs to uh, what is that formula? What is that formula? N to the power C pi, right? So
Yeah.
3 to the power C pi. So so what is that? 3 to the power 4. What is for rho 0 C pi? C pi is basically a number of cycles are there. So
One second.
there are 15 cycles, right?
Yeah, yeah, there are 15 cycles.
Then for row 120 there are 4 cycles.
4.
Then for row 240 there are 4 cycles. So this should be the answer in this way. And we can do also by one side lemma. Is it clear?
Yeah.
So how to do by one side lemma? Same thing, right?
Yes, yes.
So what is the fixed point of row 120? You have to count them, and then basically each point have 3 choices of coloring. So do same thing.
Yes. And this way it's more direct, I suppose.
Yes.
Yeah.
So yeah. So do I need to by one side lemma, or also this is clear?
This is clear.
Okay. So let's go ahead. Do some next problem. Uh, so then uh, so second question. This is saying let H be the graph below. What is the graph? Graph is this. Then we have 3 is this from here and 2 is this from here, and there is a one connecting it. So let's name the vertices. This is my V1, this is V2, this is V3, this is V4, this is V5, this is V6, this is V7, this is V8. Right. So this is the graph. Then the problem is asking find the number of ways to color the age of H, ages of H using 3 colors. 3 colors where 2 colorings are identical. Identical if H has an automorphism that takes first coloring to second one. So have you understood the problem?
Uh, Automorphism that it says first coloring to the second one. This part is a bit complex.
Yeah. So this is saying suppose you have 2 colorings of this graph H, which I am saying. So suppose you have 2 coloring. So they are said to be equivalent if there is a automorphism taking these two another one. Basically, suppose you have one coloring of this graph H, let's say H1, and another coloring, let's say H2. These two are said to be equivalent if there is a automorphism of this graph which taking H1 to H2. This means.
Okay.
So this is same thing, right? You have to identify a group and then same thing.
Yeah.
So what is the automorphism group? Can you see?
Mm.
What is the automorphism group for this graph? Can you think?
So
Yeah, you are saying.
the reflection uh, will be automorphism group, I think.
Reflection maneuver, where you are sending what
Along the
vertices and where you are sending vertices.
uh, so so the reflection the vertical reflection along the point V1, I suppose. So
So V1 you are taking V1 only and then you are sending V2 to V3.
yeah, V1 to V1 and V2 to V3, V4. Uh,
But that is not correct, na? Like
yeah. So yeah, it's not symmetric.
yeah. Think something. If there is some automorphism, then what are preserved under this automorphism of graph? You
So
can think in this.
adjacencies between
Okay,
it.
let me give you more hint. Suppose there is an automorphism where this vertex v1 can go.
It has to be adjacent to V2 and V3.
It has to be adjacent to v2 and v3. And what about its degree?
It has to have degree 2.
Yes, it has to have degree 2, right? So what
But
are
the
the degree of
places,
the vertices? What are
uh,
the degree of the vertices in this graph? This vertex has degree 2,
2.
and this vertex have degree 1, 2, 3, 4, 5. No? 5.
This is the only place for it, I suppose. Then, yeah.
And this have degree 4,
4
and remaining one have degree 1, right?
ones.
So what are possible automorphism? Now you can think, I guess.
Yeah. So basically, the leaves can shift. All other things stay the same.
Okay. So what are the automorphism group
So
basically? What is
so
the automorphism group of H? Can you see now?
we have 3, 4, 5 leaves. So
Hmm?
basically, all the combinations of them.
Combination of what?
The leaves, we can interchange the leaves however we want, and
Can
each
you
one.
interchange 4 and 8?
I mean, no. So under the vertex, the V, so V2 has the
Why you
leaves.
cannot interchange 4 and 8?
Four,
Because you cannot interchange v2 and v3, right?
yeah.
Yeah. So what are the possible interchanges?
So V4 can go to V5, V5. So V4, V5, and V6 can be interchanged
So yes.
between themselves, and then
So
V7
we
and
have a
8 can.
symmetry. Yes, we have this thing. Automorphism group is a this thing. Symmetries of 4, 5, and 6, and symmetries of product with symmetries of 7 and 8, right?
Yes.
So what is the cardinality of odd H? This is what? What is the cardinality of symmetries of three symbols?
So this is
This we discussed last time, right? Symmetric
the,
group.
so yeah.
What
This
what
is
is the
6,
cardinality of symmetric group on three symbols?
6, right? I'm not.
Yes, 3 factorial.
Yeah,
6.
6, and
And
this
this
is
is
2.
so this is 12.
Yeah.
So now we have to find out, we have to use same result which you used above. So we need to write all permutation basically, right? Because we want to use the same result. So what are the all possible permutation? So 1 should be fixed, 2 should be fixed, 3 should be fixed, and 4, 5, 6 there are possible interchanges. And then two ways, let's say one is this thing and another is I will write later. Okay, so what are the possible ways basically? So you can I will keep this thing as a this way, 1, 2, 3 are same thing. Then you can do 4 and 5, 6 can interchange. Then 7, 8. You can write all 12 permutation. That's what I'm saying. So
Yes.
then 4, 5, and 6, and this thing same, this thing same. Then uh, what? 4, 5, and 6, and this thing same. Then what? 4, 6 interchange कर दो.
Yes.
4, 6, and 5, 7, 8. What else? We have one more, I guess. We should have one more. What is remaining? 4, 5, 6, and 5, 6, 4 is remaining, right?
Yeah.
No, sorry, 6, 5, 4.
4,
6, 5,
2,
4.
6.
6, 5, 4.
Uh,
Yes, all are done. So similarly for second one, 6 are here from here, 6 will be from second one, right? 1, 2, 3. And then just take the play with 7 and 8 as well.
yeah.
4, 5, 6, 7, 8. In this way.
Yeah. Same for every other.
Yeah. So can you now you need to use the same theorem. So so number of what we need to find out, different coloring So number of required colorings is what? 1 by 12,
Yeah. Sum
and
sum sum
sum
over
over all these things. N to the power. What is n here? 3.
n is
N
3.
is 3 colors, and then number of the permutation they are occurring. So summation, this is 3 to the power. So you need to write all 12, I guess, then. So then, yeah, just write. Okay. So these are same thing. Let's do this. So how many permutation in first one? So first one we have 3
6 6.
and 3, 6 permutation. Then second one uh, we have 7
So
permutation.
let's write the it's the right hand side. So we
Completely. Oh, yes. Okay.
so
Four,
it will be
four.
quicker. No,
Yes.
no, not that. In the
Huh.
sum. In the sum, so I was saying, let's write that 3 to the power 6, then the one where the 7 8 goes together, one less, so 3 to the 6 plus 3 to the 5, so we don't need to go read once again for the second part.
Okay. Okay. Fine. Okay. Let's do in that way. So then
3 to
right
the
hand
power
side
5,
will be
3 to the power
3
5,
to the power.
one less just
Yes.
in each
Yes.
case.
Yes. So then in second one, we have
Yes,
7 permutation. So 3 to
yeah,
the power 7 plus 3 to the power 6.
6, yeah, then 3 to the power 8, the
Then
next
3 to
one,
the power 3 to the power 8 plus 3 to the power 7.
7, yeah,
Yeah, then next one we have 3
3
to
to the
the power
power
7.
6,
Then 3 to the power 6 plus uh, did I miss something? कुछ गलत तो नहीं लिखा है ना?
so the third the 3 to the power 7 in the second line, which one was it for?
First one is 3 to the power 6. First line is 3 to the power 6. Second line is 7. Third line is 8. Right?
Third
Third
line
line
is,
have 8.
yeah, yeah, yeah,
Third line have 8. And fourth line have should have 7.
yeah,
Fourth line have 7.
yeah.
Fifth line should have
Also
what?
7.
Fifth line also have 7.
Yeah,
And then sixth line have 6.
3 to the
So
5.
this is all.
Yeah.
Huh. So let's go to next problem. Where is this problem sheet? This is the question. Consider following two cross four grid consisting of 8 tiles. First one is saying, so what is the grid? The A part is saying find the cycle index polynomial of the grid under its two rotational rotational, and 2 reflectional symmetries. So the problem is asking, so consider the 2 cross 4 grid consisting of these 8 tiles. And first part is saying that find the cycle index polynomial of the grid under its 2 rotational and 2 reflectional symmetries. So can you do this? We already recall what is cycle index polynomial.
Uh, so uh, uh, each of the there will be mm, so should we first write uh, um, where each element of the group is represented by which term in
Yes.
the
First, we
polynomial?
need to write the group.
Yeah,
What is the group exactly, right?
yeah.
So what is the group?
So it will have an identity.
Which is basically rotation by 0 degree.
Yeah.
Then you
Then
have rotation
yeah,
180 degree
180-degree,
and 2
270.
reflectional symmetries, basically vertical and horizontal. So vertical, let's say uh, RV and horizontal RH. So we have this group, right? So let's name by tile 1, 2, 3, 4, 5, 6, 7, 8. We have these 8 tiles. So what we need to find out? We need to find out cycle index polynomial. So for finding cycle index polynomial, we need to find out cycle index monomial, right? So what is the cycle index
So
monomial?
is the group this only?
Yes, only this
Can we
only.
not say apply the rotation and then deflect?
But he given under its 2 rotational and 2 reflectional symmetry. It have only 2 rotational symmetries
Okay,
and 2
okay. So yeah. So okay. So because it's defined only the two
yes,
real
it is
symmetries.
defined in
Okay.
this way only. Yeah. So can you think now?
So
What is cycle index monomial for rho 0? Z of rho 0. What is this?
uh,
What is cycle index monomial? First we define monomial, then we write polynomial, right?
yes. So
So what
the
is,
monomial will consist of terms where each so say z x1 x2 and so on, where x1 represents x1 will have its power representing the number of cycles of length 1.
yes, number of one cycles, right?
Yeah, yeah.
So so
So
so what
similarly
is
for
so what is Z rho 0?
so it will have x1 to the power so that's 1, 2, 3, 4, 5, 6, 7, 8, right?
Yes, x1 to the power 8. What is Z of uh, rho 180? What is
So
Z of, what will happen by rotation by 180? Hmm?
yeah, so one will go to 5, two go,
Yes,
so we'll have four cycles of length 2,
we have 4 cycles of,
length 2.
yes. Then what is Z, sorry, of RV, rotation, reflection along vertical axis? This one should be, na? Reflection along this one, this axis. What will be?
So 1 will go to 4, 5 will go to
Yes,
8, 2 to 3,
yes.
6 to 7. So
So we have
again it will be uh
x2.
yeah.
And what is Z of horizontal reflection?
It will also be the same, right? 1 to
1
5.
goes to 5, 2 goes
Yeah,
to 6, 3 goes to 7,
yeah.
4 goes to 8. So what is the cycle index polynomial?
So the cycle index polynomial will be the sum of these divided no, just the
So
sum of
the
these, right?
yes, cycle index polynomial of G in the variable x1 and x2 is basically 1 by order of G, what is 4 times x1 to the power 8 plus 3 x2 to the power 4. Right. Now the second part is saying find the generating series for non-equivalent colorings colorings of the tiles with colors red and blue. Blue. Right. What is the generating series?
So we substitute the colors in the polynomial.
Yes, we substitute the colors in the polynomial. Right. But the colors, how many colors we have?
Two colors, right? Under the colors.
Red and blue,
Yeah.
right? Yes, red and blue. So yes, this is the what the related to Polia's theorem, na?
Yes.
So this is basically Z G x1 will be replaced by r1 plus h1 and x2 will be replaced by r square plus h square, right?
Yes.
R plus h comma r square plus sorry r plus b b for blue, r for red, and
Yeah.
x2 is replaced by r square plus b square, and this will be 1 by 4 uh, r plus b to the power 8 plus 3 r plus r square plus b square to the power 4. Now this is the required thing, generating series. You can expand it, but that for third part we need to compute some term, because third part is asking number of non-equivalent coloring with exactly 3 red and 5 blue tiles. Number of non-equivalent colorings with exactly 3 red and 5 blue tiles. Yes. So how you compute it?
So we need to find the coefficient of
Of what?
r cube b to the
R
power.
cube and B5. R
Yeah.
cube into B5, right?
Yeah.
So what is the coefficient? Can you compute it?
So it will have 8 choose
So
3.
that is basically 1 by 4. 8 choose
3 for the yeah r plus b 8.
8 choose 3.
Uh,
Uh, R power 5. R to the power 3. B to the power 5. And what? From
and
second
then
term?
yeah that will be uh, 3 times so r square and b square. Okay, so r so we need 1 and 3. Oh, yeah. Okay, so yeah, that will be 4 choose 1, right?
So from second term, anything? Second term, nothing. Okay, what will come? From second term, nothing will come for
Nothing will
R3.
come.
Yes.
Yeah.
So this will be only this thing. So let's compute this one. So this is this thing only. So what is this? What is this?
So that's r factorial by 5 factorial, 3 factorial. So that's 8766. So a 56 by 4, which
14,
is
right?
14. Yeah.
Yes. So this is the thing. Let me check, is it correct? Yes, it is correct. So now we have two types of problems. First two, which kind of problem? One problem is related to Polia's theorem and another one is, let's finish this Polia's theorem, then we'll go to this generating function and type generating function and all these things. One problem is relating remaining this of this Polia's theorem. So let's finish this first. So this may be tricky also, some part at least. I don't know because I didn't try. Consider the benzene molecule. We know benzene have 6 carbon and 6 hydrogen, C6H6. It is my it is looking as it is possible to replace hydrogen atoms with chlorine atoms, hydrogen atoms with chlorine atoms, hydrogen atoms with chlorine atoms to form new molecule, to form new molecule. Since symmetric replacement cannot be distinguished since symmetric replacement cannot be distinguished chemically, we want to find the number of molecules we want to find the number of molecules that are chemically different different after replacing k hydrogen atom with k chlorine atoms. Replacing k hydrogen atoms with k chlorine atoms. Find the generating function for this. Find the generating function for this intersection of dihedral group of symmetries. action of dihedral group of symmetries, and hence find the find the number of distinct molecule after replacing four hydrogen atoms. Distinct molecules after replacing four hydrogen atoms. So what is the problem? So once read it. So this is saying consider the benzene molecule which has the formula like oh so C6H6. Now he is replacing the hydrogen and saying that symmetric replacement cannot be distinguished chemically. So we want to avoid them. So want to find a number of molecules that are chemically different after replacing K hydrogen atom with K chlorine atoms. So we have to find out the generating function for this under the action of dihedral group of symmetries and hence find the number of distinct molecule after replacing four hydrogen atom. Can you do it?
So it is like so the problem is can be seen as four
Yes.
coloring
So
hexagon.
four coloring, why four coloring? I didn't understand.
No, I'm saying is it similar to that because you are replacing
Hmm.
only four hydrogen atoms, so there are six of them.
This is last part, but first we have to generating series for this, na? Then if we compute generating series, then we
Yeah,
know
yeah,
how to find it. If
yeah.
we compute generating series, then we know second part is just a corollary because we just have to find out the coefficient of this, like where the chlorine power is 4 and hydrogen power is 2 because 4 hydrogen are getting replaced by 4 atoms of chlorine, right?
Yes.
So first part is we have to work out first part basically. So what is a benzene molecule? Benzene is this thing, no? This thing. So and each point a hydrogen is attached, each corner. So now he is replacing hydrogens. So what is its a symmetric group? So its a symmetric group is we know its symmetries are what? Dihedral group D6, symmetric of regular six gone. This is D6. What is this? Rotation along 0 degree, rotation along 60 degree, rotation along 120 degree, rotation along 180 degree, rotation along 240 degree, rotation along 300 degree. And then reflections. So reflections around. So what are its reflection symmetries? Can you see?
So so there are
First
along
one
the
is this one.
vertical axis, yeah, and the two diagonals,
Only this much,
the two diagonals.
but only this much. Nothing more than this.
So I mean, you can also reflect along the axis that cuts through the edges in the middle and
Yes.
similar to the two diagonals.
Yes. These are its all symmetries. So basically, its first one is F0, then reflection along this 0 degree line, vertical line, then F30, then F60, F90, F F120, and then F150. Basically, right? One, two, three, four, five, six. So we have six things. So we have six symmetries, right? So now can you see how to first what we have to do? We have to find the cycle index polynomial, right?
Yes.
Then we can do basically replace by x1 by like like hydrogen plus fluorine, then so on so on, right?
Yeah.
So what is its cycle index polynomial? We need to find first cycle index monomial. So what is ZR0? Rotation along 0 degree.
That is the identity of it will contain six one cycles.
Ah, just 1 second. Ah. Yes. So, so what is this cycle index monomial for rotation along 0 degree? So this is basically x1 to the power what? X1 to the power what? Each corner we have one
Yeah.
hydrogen, and so x1 to the power 6, right? Then ZR60. What is the cycle index monomial for rotation along 60 degree?
So three cycles of length 2.
So this angle is 60 degree, na? So yeah. So what we have for 60 degree?
So three cycles of length 2.
No,
No, yeah, sorry, yeah. So
this
so
will
one
be
will
one
go
will
to
go to.
one yeah, only one cycle of length 6.
So one will go to three, three will go to five, five will go to this one. Like let me name. So let's name. This is A, this is B, this is C, this is D, this is E, this is F. So A will go to B, B will go to C, C will go to
Yeah,
D. So
yeah, yeah.
this will be
It's
one six.
one cycle of length 6, right?
Yes. So this will be six cycle of length one. Sorry, one six cycle, right?
Yeah.
X6 to the power one basically, right?
Yes.
So what is ZR120?
So 1 will go to 3, 3 will go to 5, and then 5 will go back to 1. So three cycles.
So 120 basically you are going to one will go to five, five. So A will go to E, E will go to so A will go to C, C will go to E. Yeah. So we have two three cycles, right?
Yes.
So, so X3 square. So what is Z 180?
So one say suppose so 5, and then yeah, so one for there will be one four
We
cycle.
have similar, right? Huh.
It will
We
be
have
one there will be one four cycle and then uh
five. We have one four cycle. We are rotating along 180 degrees. So A will go to D, B will go to E, C will go to F. Right?
okay 180, yeah.
So we have three two cycles, na?
Yes.
So then what else? Z of rotation along 240. What is this? What is
So
this?
here uh A will go to one second, excuse me.
What is this? Can you tell me?
Yeah, I had to go
Yeah,
ahead
but
with, yeah. So what
you
were you
have
saying?
to. Okay. Okay. So what is this? So this is basically 240. So A will go to E and E
Yeah,
will go
yeah.
to.
B will go to F, C will go to uh, A, and then D will go to B.
So A will go to E, P will go to F, C will go to. This is something missing. Some we are doing something wrong. So rotation along 240 degree. So how many permutation we have? So if A is going to E, then E will go to where? E will go to along 240 degree where? This will go to E and C will go to A. Yes, we have 3 cycles.
Yes.
So x3 square, then rotation 300. So what is this? So this will be 1/6 cycle basically. X1 so 1/6 cycle. So x6 basically. So what is cycle index polynomial? Is there some background noise coming?
Sometimes.
Yeah, maybe because I'm not in campus, so there may
Right.
be some interactions. Sorry for that. So ZZ is 1/12 because the order of group is 12, and then sum of all these things, which is basically x1 to the power 6, then we have 2x6, and then we have x3, 2x3 square, and then we have x2 cubes, and similarly for this one f0, f3, f30, f60, f90, we have to compute all these reflectional symmetries as well. So yeah, so just compute these things. So what are the for reflectional symmetries? So this is the do similar computation for reflectional symmetries, right?
Yes.
So we will get required cycle index polynomial. So then, yeah, there is no problem in calculation. Na? You can do that.
Yes.
Na?
Okay. I can do
So
that.
this is cycle index polynomial, and then what we need to find out is that we have to find out the number of distinct molecule after replacing 4 hydrogen atom. So once you are getting 4 hydrogen, once we are replacing, so we have to find out what we have to find out number of. We need to find number of distinct molecules after replacing after replacing 4 hydrogen atoms. Huh. So we have to find out the number of distinct molecule after replacing 4 hydrogen atoms. So basically, so we have to find out. So this is basically find. So this is how we will do. Replace x1 by hydrogen plus chlorine, x2 by H2 plus Cl2, and so on, so on, so on. X6 is S6 plus Cl6. Then we have to find out the coefficient of H2Cl4, right? So basically we have to replace 4 hydrogen atom by 4 chlorine. So find out so find out coefficient of H2Cl4 in equation star will give will give required number of molecule. This will give required number of distinct molecule. Number of distinct molecule. Right. Yes. So is this clear?
Yeah.
Yeah. So let's do some more problem because we have half hour at least. So because yeah. So Let's do one more problem, then we will stop. So this is about species because we doesn't till now we did some application of Polias theorem, some about one-side lemma, and so on, so on. Some like cycle index polynomial, all these things. So now let's go to this species thing. So, so first problem is about finding the generating series and generating function. Sorry, type generating series and okay. This is the question. Find generating series and type generating series of the following species. Find generating series and type generating series of the following. First one is first one is power set of x. The species taking any x to its power set to px. You are familiar with what is power?
Yeah.
Yeah. The second one is about, let's say, about permutations of x, sx, permutations of x. Third one, say, let's linear order of x. What is the notation? Lx, I guess. So let's find out the generating series and type generating series for all these things. And if there is some more time, we will do some more things. Linear order on x. So let's do first one. So can you think how to do first one? This is a new type problem because till now we are doing one-side lemma on all these things. So how to compute generating? Let's first think about generating series for px. So generating series is fn x to the power n by n factorial, right?
Yeah, so Fn would be 2 to the power n,
So fn is
2 to the power
2 to
n.
the power. Yes. So what is this series basically? We have the generating series for species px is equals to summation 2 to the power n x to the power n by n factorial. This is what? This is summation n greater than equals to 0, 2 to the 2 x to the power n by n factorial. And this is what? This is what? This is the expression of what? E to the power 2x, na? You know the exponentials?
Yes, yes,
Ex-
yeah. I know.
Yeah, yeah. So what is the type generating series for this one? Px?
What will what so my how do we what by what criteria do we assign the isomorphisms here?
What do you mean by that? I didn't get. So
So
you,
the equivalence classes.
uh,
Here
two sets are said to be equivalent if there is a like if what is the definition basically? I told you initially, right?
there's a
So what is
bijection, right?
yes, yes.
Each set. Uh,
So basically the same cardinality set you always have there is a bijection, right?
yeah. So each set will have uh, how many? It's one less, right?
I didn't get what you are saying. So each
So
for each and you have n plus one choices basically, right? Because for each and you have either this set can be empty, either this can have one cardinality, this subset can have two cardinality, or at most can have n cardinality, right? So you
yes,
have n plus one choices. Because if two sets have same cardinality, they are going to be equivalent. There is going to be some bijection there, set
yeah,
theoretic
yeah,
bijection,
yeah,
and that will induce bijection on the level of species, right?
yes.
So so what is two sets? Since two sets are equivalent, if and only if they have same cardinality. Two sets are equivalent if and only if they have same cardinality. So, 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 yes. So, so f and tilde is what? N plus one. So we will get required this thing, right? So type generating series is summation n bigger than equals to 0, n plus 1, x to the power n by n factorial. Sorry, x to the power n, because in this thing, this is formal expression, not exponential. So what is this expression? Hmm? Can you see? What is this expression? This doesn't. Okay, fine. Anyway, this is the type generating series for this thing. Let's do some other. Okay, so I already write some others here, right? Other cases. So let's compute them also. Then we'll wrap up there. If
This is
oh
1 over, I think, 1 minus, this is n plus 1, right? Yeah. 1
yeah,
over
n
1
plus
minus
one.
x square.
What you are saying? 1/?
1 minus x square, whole square.
This thing?
Yeah.
What is?
Yeah. I think
Uh,
I can't remember correctly, actually. It's a
I
guess.
doesn't. I don't think this should be. I don't think this is correct.
Okay.
It shouldn't be correct. This will say that 1 plus 2x plus. Maybe this is correct. Maybe this is correct. Maybe okay. You can just check. I'm just writing it as a black box.
Oh,
Just check it. Right? This will some binomial expansion and open it and check it. So next one. So second part we have permutation of x. So Sx basically, right? So what is generating series for permutation Sx?
n factorial. So the fn will be n factorial.
Yes. So what is the generating series? Generating series will be fn x to the power n by n factorial, which is summation x to the power n bigger than equals 0. This is what?
Uh,
This this is what? 1 upon 1 minus
1.
x, right?
Yeah.
Because if you open the expression, this will be 1 plus x plus x square and so on, so on, so on. And this is precisely this thing, right?
Yes.
What is the type generating series?
So permutations will have
When two
so
permutation are
all,
equivalent.
yeah, all the n, right? So
Yes.
the
For
fn
yes, suppose you have two permutation on n symbol when they are equivalent.
say again.
Suppose you have two permutation on n symbol. Let's say sigma and tau belong to Sn. When they are equivalent, that's what we need to count for Fn. Na?
We have two permutations on
N symbols, basically Sn, two elements of Sn, symmetric group on n symbols.
yes, but if
So when
we
they
have a
are equivalent,
bijection,
we have a bijection of what?
bijection,
Of sets taking one permutation to another permutation, right?
yes, yes,
So basically, I am saying you this thing, right? Suppose you have one permutation, 1, 2, 3 in S3, and another permutation, 1, 2, and 3, and another permutation, 3 going to 2, 2 going to 1. See, we have three permutation in S3, right? These three are in S3, right?
yes,
Which of them are equivalent? Which of them are not? Can you see?
yes, the ones with the same cycle structure.
Yes, same cycle type basically.
Yeah.
So how you concluded that?
So because the in the permutation if we map
One, two, three, two, 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 three to one. Then we have basically this thing, na? Taking
yeah,
one permutation to another. But
yes,
in second case, other case we can't have, right?
yes,
So yeah. So two permutations are if they have same cycle type. Yeah. So basically, so suppose you have an n symbol. So what are the cycle type possible basically? So either you can have, so suppose you have three, it's n equals to three. So what are the possible cycle type? So either you have three, or you have two one type, or you have or you have like one 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 type. These are the all possible type in three case basically, right? You have
yes,
all three cycles of length one, or can have. So this is basically partition of n, right? For each
yes,
n, the two permutation are equivalent if they have same cycle type. So Fn equals to partition of n, natural number n. So what is the what is the ftidal n? So what is the type generating series? So type generating series is summation n greater than 0 fn tidal x to the power n, which is summation n greater than equals to 0 pn x to the power n, and this is known to be product of k bigger than equals to 1 1 over 1 minus x to the power k. So yeah, this is the expression you have to, like, this may take, will take effort basically. Power series of pn x to the power n is this thing. This will take some effort in proof. This is the are you familiar with this Weyl conjecture stuff? So this comes
say again.
this are you familiar with this Weyl conjecture which
No,
Andrew
no.
Weil proposed? So this thing, all things are used there in number theory course. So maybe you, this is a basic part of that. I'm not a part of Weyl conjecture, but in the basic theory, this type of equality you proves there.
Okay.
So yeah, so yes. So then what else we need? एक प्रॉब्लम और लिखा था ना हमने, पावर सेट and linear order.
Linear order.
Le yes. So what is the for linear order? Generating series for linear order?
Same as permutations, I think.
How?
Because you are mm,
What is the linear order? Do you understand the meaning of this?
linear. So I don't remember exactly, but it was basically forming a line, right?
Forming a line.
Line with
Intuitively, that
elements.
is correct. But what you mean by line basically? Uh,
So
yeah, intuitively that is correct because you are
sequence of
comparing this with a real line and you will say you have ordering with on real line. But what is the definition? This doesn't seem to me correct. Yeah, maybe intuitively it is correct, but not precise. Yeah. So what is the
yes,
definition of a linear order? Can you recall? So linear order is basically, so you are familiar with the definition of coset.
yeah.
So a coset in which any two elements are comparable.
Okay,
Either
so that
you
was
can say either x is less than y or y is less than x, or they are equal.
the total order, right? Yeah, yeah,
Yes, linear order or total order. Yeah.
yeah.
So now can you say why this is same as you are saying sx basically?
Yes, because in if any two are comparable, then we can permute between them. So because there's no restriction in which to how you can choose.
Can you say again what you're saying?
So
Suppose I have a linear order on n symbols. So now you have to say that this is same thing. Giving linear order on n symbol is same thing. Giving permutation on n symbol. Basically, that's what you are saying, na?
yes,
So how you will say that? Suppose you have n elements I1, I2, so on, so on, so on, In. Now you are giving a linear order to these n things, right? And a permutation to these n things. You are saying these two are same thing basically.
Yes, yes.
How? Your justification is not clear to me. Can you say again what you are saying something, but I doesn't
Okay,
what you are.
let me 1 second. Let me formulate it a
Uh,
bit clearly.
okay, so if not, should I tell?
Yes.
Okay, so so if you have given any linear order on L in, let's say I1, I2, In. So what I am doing is that basically, okay. So let me write. So given linear order on of n elements and let's say I1. So basically इनका linear order देने का मतलब एक ordering देना. This is the ordering let's say I gave. So I will define a map sigma which takes I1 to 1, I2 to 2, I3 to 3, In to n basically, and give corresponding ordering here. So this will determine a permutation, right?
Yes.
Similarly, so on, so on. If you have I1, I3, I2, then basically 3 goes to 2 in similar way.
Yeah.
So then basically this sigma inverse is precisely the linear ordering, giving the linear order to this n symbols. Are you getting or not?
Yes, I'm getting.
Yes.
So,
Yeah.
yeah, it makes sense.
So and we have already computed. So uh, basically what I'm saying is that under sigma inverse, this will give the linear ordering there in that way. So what I'm saying is that under sigma inverse, the order is equivalent to order 1, 2, 3, n. The order is given by the order of 1, 2, 3, n. Order of 1, 2, 3 up to n. So hence the equivalence class has only single element. Sorry. What I'm saying, I am doing not for equivalence class. I am doing for this thing. So I have to, yeah. So this is same thing. So that means, so the generating series. So generating series Sx is equals to Lx is equals to what we have computed already, which is 1 minus x. Now type generating series. So for type generating series, what we need, what happen in permutation is that two permutation are equivalent, are getting equivalent if they have same cycle type. But what about their linear order? Are they will their linear order will also be equivalent?
Hello, am
Why?
I audible?
Hmm?
Am
Yes,
I?
yes, you are audible.
Oh, yeah.
Yes,
Can
yeah.
you repeat your question again?
So we see that generating series for Sx and generating series for Lx are same. So I am saying that we already computed the type generating series for Sx, and now we have to compute type generating series for Lx. In computing the type generating series for Sx, we have seen that like if they have like two permutation are equivalent if they have same cycle type. So I am asking whether two permutation have same cycle type, they will give same linear order or not. I am saying this thing.
Okay, no, I don't think they are the same.
Why?
Because, well, the automorphisms will be different in permutations and
Yes,
in related.
yes,
Yeah.
yes. Because this linear order will be is given by the ordering of the natural number 1 to up to n. Na?
Yeah.
So it's inverse map. So so these two are not equivalent. Basically, these two are two permutation. As a permutation, they are equivalent, but as a linear order, they are not equivalent because the linear order is coming from the order of natural number.
Yes. Yes.
Yeah. So the type generating series for this remains same. So which is basically st del x, lt del x basically. LT del x, which is already we have computed above, which is n greater than 0 x to the power n, and which is 1 by 1 minus. Sorry. What I'm doing? Sorry, what I'm doing? Type generating series we have to compute. So we have to compute fn tilde, fn tilde, fn tilde. We have all things are going to be equivalent, na?
Only one
All
automorphism.
all linear orders are going to be equivalent because these linear orders are going to come from this one sigma inverse. So
Yes.
I, if you give me any linear order on n symbol, let's say sigma 1 and sigma 2, what I will do, suppose you have, let me say here, suppose you have one linear order I1 less than I3 less than I2 less than so on In, and another linear order, let's say I1 less than I4 less than this linear order, let's say, right,
Yes.
In. So what I will do, I will define a map from here to this one goes to 1, 3 goes to 2, I3 goes to 2, I2 goes to 3, and so on, and then define map from here to here. 1 goes to 1, 2 goes to 4. This will prove that these two are equivalent, basically.
Yes.
Yeah. So all linear. So so I should say. Are you getting or not?
Yeah.
If not, you can ask me, right? Because uh,
This is
yeah, like
this is
I am
basically
not
that
in campus. I am at home, so basically I got some disturbance also. So yeah. So
this
so
the idea is basically that there is only one automorphism class, right?
yes,
Every,
that's
they are
correct.
all
So basically, all orders are the idea is that all orders are coming from order of natural number by this sigma inverse, basically. So if there is any order, let's say I1, I4, In, so I will define a map sigma, which is 1 goes to 1, 4 goes to 2, so on. And this
yeah.
order is coming from 1, 2, 3, basically, right? Under sigma inverse.
Yes.
So so since all orders are equivalent, thus thus fn tilde equals to 1 for all n. This will imply summation fn tilde xn n greater than 0 is equals to summation n greater than equals 0 x to the power n, which is what? 1 by 1 minus x. Yeah. Anything else we have to do? Let's do for species of sets and then wrap up things. Last one. Compute the generating function and type generating series for species of sets. Huh. So just do it quickly, then okay, then we'll stop there. So what is the generating function for species of sets? Can you see?
The for species of sets,
Yeah. So what is Fn? Fn,
so
number of sets with n elements.
num one.
Yes.
Oh, no, sorry. Yeah.
Number of set, that is one, na?
Yeah. One.
And so what is your generating series?
1 over. So that's the exponential one.
Yeah. Generating series is by n factorial, which is ex. And what is type generating series?
Uh, type gen type genesis will be 1/1 minus x for this, I think. Yeah,
How?
because the type is also one, right? And but this is the ordinary one, so it will become,
Yes.
yeah.
Type is also one because there is only one, so equivalence relation is going to kill out nothing, na?
Yeah.
So summation n greater than 0, x to the power n, which is 1 by 1 minus x, right?
Yes.
So okay, let's stop here. Uh, Let me stop recording.